Good morning. This is a recorded remedial session to cover the revision for units 1.6, 1.7, and 1.8 of the chemistry AP. We start with the first question, which is a free response. Here in the figure, it shows a photoelectron spectrum. I want you to know that for the photoelectron spectrum, it shows the amount of electrons, the number of electrons versus their binding energy, the energy which that we need to give the atom in order to remove an electron. That's the binding energy. So if I look at an atom, it has the nucleus inside, in the middle of it, with protons, and around it there is the electron cloud with the electrons. So every electron is attached to its own orbital and energy level, and we need a certain energy called binding energy in order to remove that electron. Now this electron is affected by the attractive pull coming from the nucleus. Now the electrons that are close to the nucleus are called the inner electrons, whereas the electrons on the outermost energy level are called valence electrons. So for example, this is the last energy level. This is a valence electron, whereas all the electrons in here are inner electrons. The inner electrons are more and more affected by the attractive pull of the nucleus. And also, in other words, the further the electron from the nucleus, the less its binding energy. The closer the electron to the nucleus, the higher the binding energy. So when we look at this graph, we see on the x-axis binding energy decreasing. So here it's a 1,000, 110, and 1, which means that here are the electrons that requires less energy to remove them. So most probably these are the valence electrons, and in here these are the inner electrons that requires more energy to remove them from the nucleus. So, and in the electron configuration, the way electrons are arranged is the following the electron configuration 1s2. So we start giving the highest binding energy to the inner electrons. So that's the peak of 1s2, and that's the peak of 2s2. And after the 2s2 comes the p with 6 electrons, 1, 2, 3, 4, 5, 6. So that is 2p6. Again, this is a 3 with the same height, so this is 3s2, and this is a 3p. However, this 3p is not as long as much as the 2p6, so that makes it 1, 2, 3. 3p, 3. Therefore, the electron configuration, identify the unknown element and write its electron configuration. Here's the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p3. That makes it 15 electrons, and this is phosphorus. So the atomic number is 15, and the element is phosphorus from the periodic table. Moving on. Now, consider the element in the periodic table that is directly to the right of the element identified in part A. So here's the periodic table, and I have here aluminium, 13 electrons, silicon, 14. I have phosphorus, 15, and I have sulfur, 16, chlorine, 17, and argon, 18. So which element are they talking about? They are talking about the element that is to the right of the identified one. So here's the element. So it is sulfur. So they're talking about sulfur atom. Okay, so would 1s peak of the element appear to the left or right or in the same position of the 1s peak of the element in part A? Let me change the color and show the peak of sulfur with the red. Now, let's look at the effective nuclear charge. Compare the effective nuclear charge or the attractive pull of sulfur and phosphorus. Phosphorus has 15 protons in its nucleus, whereas sulfur has 16 protons pulling out, attracting out the valence electrons. However, the shielding effect for both of the atoms is the same. So here, the electron of 1s that we are talking about are having the same shielding effect but different attractive pull from the nucleus, different effective nuclear charge. So electrons in S are more attracted by their nucleus because their nucleus is larger, and therefore 16 protons, and therefore removing 1s from S requires more binding energy compared to removing an electron from the 1s of the P. So going this direction on the peak requires more energy. Going this direction requires less energy. And if I draw it on the same peak, that would be the same energy. So the peak of S would be to the left of the peak of P for sulfur. Okay, so here I should write my answer. One second. So in the reasoning, when you explain your reasoning, so you have to mention it clearly. Okay, so first the peak would be to the left. That's one point. The peak would be to the left of the peak in the spectrum, and as an explanation you would say that 1s electron of 1s of sulfur have or exposed or has higher binding energy. 1s of S is 1s electrons. Wait, let me write it in a proper way. The nucleus of sulfur would have more protons than phosphorus. Therefore, the binding energy and the effective nuclear charge will be higher. Okay? Now another question. Also the same topic about the photoelectron. So here's the photoelectron spectrum of an element is shown above. Which of the following observation would provide evidence that this spectrum is consistent with the atomic model of the element? So let's look at the choices given on the next page. So a neutral atom of the element contains exactly 2 electrons. I see 2 peaks on the previous page. There were 2 peaks. Let me just write the configuration here. So I have 1s2 and I have 2s1. So that would be lithium 1s2 and 2s1. So a neutral atom contains exactly 2 electrons. I'm sorry, that's not correct. The element does not react with other elements to form compounds. Definitely no. Elements of group 1 are very reactive. In this compound, the element tends to form ions with a charge of +1. Yeah, that's an answer. In this compound, the element tends to form ions with a charge of +3. It must be in group 13 to choose this choice. So the correct answer is C. Next, moving on. Another peak. Also, always look at the binding energy. The peaks with higher binding energy are the inner electrons. So 1s2, 2s2, 2p6. You follow the order of the electron configuration. 3s2, 3p. Again, this is 3p3. So the complete photoelectron spectrum of an element given above, which of the following electron configuration is consistent with the spectrum? So that would be B. Again, another question. The photoelectron spectrum of the binding energy, which of the following best explains how the spectrum is consistent with the electron shell model of the atom? So let's see. This is 1s2, this is 2s2, this is 2p3. So in this question, the leftmost peak represents the valence electron. The leftmost peak represents the inner electrons. That's not correct. The 2 peaks at the right represent a total of 3 electrons. That's not correct. I have a total of 5 valence electron because this is the highest energy level. The electron in the 1s has the highest binding energy. That's wrong. And finally, the 2p electrons has the smallest binding energy. Exactly. Because this is the furthest from the nucleus. Now, moving on. One more question. Which of the following best helps explain why the electronegativity of Cl is less than that of F? Okay, so if I look at the electronegativity trend, the electronegativity trend increases as you move in across a period in the periodic table and decreases down a group, or from down to up it increase and increase. And the highest En and the highest element of electronegativity is fluorine, F. The noble gases are not related. Noble gases, their electron energy, electronegativity is 0. Okay, so what's the reason why F? So what's the question again? What's the reason that the electronegativity of Cl is less than that of F? So the mass of Cl atom is greater to the mass. Electronegativity is not at all related to the mass. So that's wrong. The Cl nucleus contains more protons than the F nucleus contain. This is true. F has 9 protons, Cl has 17, but this has nothing to do with the atom loving more electrons. So I'm gonna discard this choice. When Cl and F form bonds with other atoms, the Cl bonding electrons are more shielded from the positive Cl nucleus, then the F bonding electrons are shielded from the positive SF nucleus. And that is exactly correct, because if I look at F has two inner electrons. F has two inner electrons doing the shielding effect, whereas Cl has 10 shielding electrons, 10 inner electrons, and therefore the electrons in Cl are more shielded from the positive attractive pull of the nucleus of the Cl, whereas the 7 valence electrons of F are more affected with this attractive pull of the nucleus, and this is F has more tendency to attract electrons. Now moving on to the next question, which of the following best helps to explain why the electron affinity of Br has a greater magnitude than that of I. So the electron affinity, adding electron to Br is more releases more energy than adding an electron to I. So let's look at this. Let's look at the choices. Second. EA of Br has more magnitude than the EA of I. Br has a lower electronegativity than I. In the periodic table, I have F followed by Cl, I have Br, and I have I. So the electronegativity increases as I go up. So Br has a lower electronegativity than I. That's even wrong. Br has a lower ionization energy than I does. That is wrong, because Br has a higher ionization energy. But anyway, this is not related. That's wrong, because En increases and ionization energy, as I move up, it increases. An added electron would go into a new shell in Br, but not in I. That's extremely wrong, because they both have 7 valence electrons, and the electron is added in the same shell to complete octet rule. And last, which is the right answer, there's a greater attraction between an added electron and the nucleus in Br than in I. So yes, in Br, the electrons are much closer to the nucleus than in I. Br, it has 4 periods, where the last electron to be added in I is added on energy level 5. So definitely it's further away from the nucleus. Now moving on, which of the following represent the electron configuration that corresponds to the valence electrons of an element for which there is an especially large jump? Okay, large jump. So when we have a large jump in the ionization energy, we're talking about a removal of electron from inner electrons and not any more valence electrons. So there's a large jump between the second ionization energy and the third ionization energy. There's a large jump. From this, you need to understand that we are dealing here with 2 valence electrons, and the third electron is an inner electron. So, which of the following would be the correct configuration? Here I have 3 valence, 4 valence, 5 valence electron, and A is the only one with 2 valence electrons. Another question, if Na reacts with chlorine to form NaCl, which of the following reacts with Na to form an ionic compound in a 1-to-1 ratio. Okay, Na bonds with Cl, Na plus and Cl minus, in a 1-to-1 ratio of an ionic compound. So if I want to answer a question like this, I would go with an element in the same group of Cl to have the 1-to-1 ratio. Magnesium, argon is a noble gas anyway, and bromine. So K, which of the following? Let me just focus on the question. K is in the same group of Na. It's not gonna bond with Na. So I need to find another alternative for Cl to bond with the Na. So Mg is a metal, Ar is a noble gas, Br is in group 17, just like Cl. So that's the correct answer. So Br needs one additional electron, just like Cl. So it will bond with Na on 1-to-1 ratio. Now another question showing metal of a group 2 and bonding to an element of group 17, the chlorine. Okay, so here in this question, all of the chlorides of the alkaline earth metals have similar empirical formula, of course, because elements of group 2, they do positive 2, so we need 2 chlorides in order to make the formula unit. Which of the following best helps explain this observation? Cl2 gas reacts with metal atoms to form strong covalent bond. A non-metal cannot react with a metal to form covalent bond. So that's wrong. Cl has a much greater electronegativity than any of the alkaline earth metals. This is true, but not the reason to why all these compounds having the same empirical formula. So not relevant. The 2 valence electrons of alkaline earth metals are relatively easy to remove. This is correct. This is correct. Yes. And that's why we need 2 Cl minus in order to make this compound. So the correct answer is C. Moving on with the questions, RBCl has a high boiling point. Okay, because RBCl is an ionic compound, and usually ionic compounds, they do have a high boiling point. Which of the following compounds is also likely to have a high boiling point and why? So let's look at the choices. NO, Cl, F, and Cl2O are all covalent compounds. Covalent compounds. So they would never have covalent compounds. And covalent compounds, they have a lower melting point than the ionic. So these 3 options, they would never have a higher boiling point. So I'm definitely not reading this choice. And the correct answer is CSCl, which is an ionic compound because its elements have very different electronegativities and it is an ionic compound. And this is completely true. Now, moving on with the choices, let's see. So here's another question. Okay, so answer the following questions related to the chemical bonding in substances containing Cl. Now, what type of chemical bond is represented or present in Cl2? Cl2 is a non-metal, Cl is a non-metal, so the type of bonding is covalent. So this doesn't need any explanation. A full mark would be earned in here. Now, if Cl2 reacts with element Sr, that's a metal. to form an ionic compound based on the properties. Based on the periodic properties, identify a molecule X2 that is unlikely to react with SR in a way similar to how Cl2 react with SR, and justify your response. So SR, when it reacts with Cl, we will obtain SR Cl2. So we need another molecule that it can react with SR in a similar way. So I need to choose any diatomic molecule belonging to group 17, just like Cl, yani to have the same chemical behavior. So that could be any element of the group of Cl. So fluorine, bromine, iodine, or astatine. So now I am, the question is asking me identify a molecule. So I should write F2, Br2, I2, or A2. Okay? Or you can earn a full mark by saying any other element belonging to group 17. The same family as group 17. I'm gonna write the answer over here to provide more space. So F2, Br2, I2, or A2, AT2. Any element in the same family, because it would have the same or similar chemical properties. Okay, now next on the graph, so a graph of potential energy versus internuclear distance for two Cl atoms is given below. On the same graph, carefully sketch a curve that corresponds to potential energy versus distance for two Br atoms. So this is for Cl2. So this graph is for Cl2. We need to draw another one for Br2. Now, before drawing, I want you to know that the peak down here is the binding energy. It's the bond. It's when atoms bond. Sorry, not binding. It's when the bond energy. And here, when they bond, the two atoms of Cl, they keep on coming. They come close to each other as they are attracted more and more and more to each other. Their potential energy is less because they are moving more toward stability, increasing stability. And the minimum distance they can be from each other is called the bonding energy. It is here where they bond. Their nuclei cannot be any more closer than this distance from each other. So as Cl and Cl are approaching together, this is the maximum distance their nuclei can be away from each other, close to each other. And therefore here they start sharing electrons. At that point, this is the maximum stability that a Cl2 can have. So this peak is called the bonding energy. Now, beyond that, the two elements, the two atoms, if they came closer to each other, they start repelling each other. And then they move away, lowering their stability. So I might record another video in my tutorials to explain also the how do we understand this potential energy diagram. So in this case, if I want to draw a curve for the Br2, the curve has to have this same shape, but the minimum value, it will have a minimum value to the right. Okay, so in this case, because the atom of Br is larger, the bond of the bond Br has a greater length. So let me see here, bond length of Br is greater than the bond length of Cl. So here's the distance. So saying here, at this point is the distance of Cl from a Cl atom. Now, Br to Br cannot be this much closer. So they might be, for example, at a further distance. So any point here. And the minimum value of the curve has to be higher. So the peak of Br must not be this much, because the bond strength, the Br, let me just erase this. Br strength, bond strength is less than the Cl bond strength. So as the length increase, the strength becomes less. So instead of drawing Br with a peak at this point, could be the peak here. So I'm going to do a curve with the blue color, with a peak here, but shifted. So could be like this. Here, sorry, my hand is not okay. So 2 points has to be clear in this curve, that it should have less bond strength and so less bond strength, so the peak is less, so it could be here, and it should have more bond length here. Moving on. Now, in the box below, draw a complete Lewis dot diagram for C2Cl4 molecule. C2Cl4 molecule. Let's review a little bit the steps in order to know how to draw a C2Cl4 molecule. So first of all, we count all the valence electrons. I have 4 valence electron in carbon. It's a total of 2 carbon, that's 8 valence electron, and 7 valence electrons in chlorine, and we have 4 elements of chlorine, so 7 by 4, that's a 28 valence electron, and eventually a total of 36 valence electron. If I divide this over 2, I am dealing with 18 pairs of electrons to distribute. So C is less electronegative than Cl. So the atom C must be in the middle, surrounded by the atoms of Cl. So let me just here. Cl, 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 and Cl. Okay, so we have 18 pairs to distribute. So first of all, connect these 2 central atoms, 1 pair. Connect the central with the terminal, 2, 3, 4, 5 pairs. Now complete the octet rule of the terminal atoms. So now I distributed 5 pairs, I continue. 6, 7, 8. Completed the octet rule of this terminal. 9, 10, 11, 12, 13, 14, 15, 16, 17. One more pair to distribute. Now, when you go back to the central atom, let's say that this is the central atom, you put it as a lone pair. However, when you look at these two carbons, you will notice that one of them completed the octet rule, but the other one did not complete. So therefore, the lone pair on the central atom will be in the middle as shared double bond. Okay, like this, both carbon completed their octet rule. Moving on to the next question. Answer the following based on the diagram you drew above. So let me just double check one thing. They asked for Lewis, yes, and this is Lewis diagram. What is the hybridization of C in the atom? Okay, let's look at the hybridization type. Every carbon here has 3 domains, and the hybridization type is sp2. I'll just remind you that 2 domains sp, 3 domains, the hybridization will be sp2, 4 domains sp3, 5 domains sp3d, and 6 domains sp3d2. Now, what is the approximate chlorine-carbon chlorine bond angle? Okay, that requires memorization. So anyway, if I have a Cl, let's focus on one carbon. Let's focus here. There's this carbon with a Cl and another double bond and another Cl. Okay, so this is a trigonal planar, and the angle of a trigonal planar is approximately 120. Now this angle could be a little bit less due to the double bond, but it's not asked. So approximately 120 angle. The next question, is the C2Cl4 a polar molecule? Oh, definitely it's not a polar molecule. Let me just draw it till the end. This is a C. This is the first carbon with a Cl, another Cl, a double bond. This is another Cl, and this is another Cl. So that's the representation of this molecule in space. Okay, so if we look at this, when we draw the dipoles, since this is a trigonal planar molecule, all the dipoles are cancelled. They cancel each other, and the net dipole is 0. Therefore, this is a non-polar molecule. Anyway, this question doesn't require any explanation. But the student has to see that there's a kind of symmetry in this molecule. Okay, now moving on to another new question. A student has a 10-gram sample. Okay, let me see in this one. Here we go. 10-gram sample of calcium bromide. I think this is a free response as well. 10 grams of this sample Br, CaBr2. Show the setup of the calculations in order to determine the number of moles of CaBr2 in the sample. You don't need to do any calculations. So let's write the answer over here. In your formula sheet given to you during your AP exam, you have a formula showing that the number of moles is equal to the mass given divided by the molar mass. So here, all you need to do is just say that the 10 grams of CaBr2 would be divided by the molar mass. And the molar mass of CaBr2 is the mass of Ca 40, the mass of Br is 100. The total is going to be around 200 grams per mole. 200 grams per mole. So it's 200 grams per mole. So 1 mole has a 200 grams of calcium bromide. Or simply just say, write this formula. Divide, or write it written, divide the given mass by the molar mass of calcium bromide. Next question. What number, in addition to the answer to part A, is needed to determine the number of atoms of A? So in order to move from mole to atom, we always multiply by Avogadro's number, because the Avogadro's number is 6.022 times 10 to the power 23 atoms or particles or ions units per mole. So whatever number I get from this division, this calculation, I can multiply it by Avogadro's number. But here I don't need to do any calculations. I just need to say that we need Avogadro's number. Now the third question. A different student is given a 10-gram sample labeled CaBr2. So I have sample 1. Usually this is a one type of question in the AP. They're going to ask you about impurities. So sample 1, you have calcium bromide with a 10 grams compared with another sample of calcium bromide of 10 grams. I'm sorry. However, the second sample may contain some impurities, and the impurities will not react. So if this compound is reacting with something else, we're gonna get less products obtained, because part of it is not going to react due to impurity. Identify a quantity from the result of laboratory analysis that the student could use to determine whether the sample was pure. So for example, if I am using this sample to calculate the mass of calcium in it, I would obtain less mass of calcium. Or if I am using this sample to calculate the mass of Br in this sample, I'm gonna obtain less mass of Br in this sample. Or if you can say, if you don't want to say mass, you can say for each either mole of calcium or mole of Br would be less obtained. So I hope you're getting the point. So usually we take a sample to analyze it. And the purpose of analyzing a sample is to determine the mass of each atom forming this sample. So if I have a 10 gram of a sample AB, I would want to know what is the mass of A in this sample, or what is the mass of B in this sample. So if this sample contains impurities, I'm going to obtain less mass of A or less mass of B. And this question is asking you what kind of result identification in the laboratory might help you know that this sample has impurities. So it could be you're calculating the mass of each atom. So you would say I would have less mass of each, or either. Or if not mass, moles. That's it. So if not mass, it could be moles. Now, part D, and finally, explain why CaCl2 is likely to have properties similar to that of CaBr2. That's so obvious. Yani Cl and Br belongs to the same family group in the periodic table. So Cl and Br, they have the same chemical properties, the same valence electrons. So definitely they would have similar properties. practice. Thank you.